this paper, and the title is InstaGAN, Instance-Aware Image-to-Image Translation. My presentation, this set of slides, should be available to you. So that would probably be helpful to have that, as well as the paper to look at while I'm talking. If you want to go ahead and bring those up. But so this paper is by 3 researchers from Korea. And it was published very recently. It is a 2019 paper. So I'll go ahead and begin. I'll present the abstract by way of introduction. It's a little terse, but we'll talk in detail about all the terms that are presented on this slide later. Unsupervised image-to-image translation has made significant advancements using generative adversarial networks, which is abbreviated and as GANs and pronounced GANs. But when the task is complex, involving large changes in shape and or multiple target instances, prior techniques often fail. So this paper has developed the InstaGAN technique. And InstaGAN uses instance information here in the form of object segmentation masks to improve multi-instance
Frank, can you go back one slide and let's start?
Excuse me? So the paper develops some new techniques and that they want to highlight, and that's the context preserving loss. And it encourages the network to learn the identity when no target instances exist. And then a practical technology that they've, algorithmic technology that they've developed called sequential mini-batch inference training. And it allows InstaGAN to conserve memory and allow the GPU training on multiple instances. And then finally, the paper presents a comparative evaluation using many examples from different data sets. So I'll begin by giving a very introductory example. And so this translation is from the domain of sheeps to the domain of giraffe. And the targets, there are 2 targets in the input domain. So you can see how it's preserved the background. But these elements within the image are translated from one domain to the other. So here's a more challenging example. This is the opposite domain transfer, going from giraffes to sheep. So in this example, you can see that there are artifacts remaining from the transformation. So that's why it's perhaps more challenging. And these artifacts, this is sometimes referred to as in-painting. There are holes in the image and you have to fill it in synthetically. So it's doing more than just superimposing images on top of a background. It actually has to learn how to reconstruct a background. I'll go into a little bit more of the paper as an introduction. The paper uses quite a bit of techniques that have been developed before. It's basically doing a lot of combining of techniques. So I'll go into some of those more fundamental ones, give you some introduction to that. But more than just what they've done in the paper, cross-domain generation is used in many areas of machine learning, machine translation, image synthesis, and text style transfer. So we talk about domains and in this paper, and so what we mean by that is it's a set with a common property, such as, for example, outdoor images in winter. Image-to-image translation does not require example translation pairs, but it needs only training sets from the source domain and the target domain. So they don't have to be pairs of training in this case. So for example, if we want to translate images from summer to winter, we don't require that the position of the camera in summer be identical to the position of the camera in winter for our training data. We only need a set of summer photos and an independent set of winter photos. So that's a big advantage to this system. It not only does it make a lot of problems practical by reducing the cost, but some types of things would be impossible. If you were trying to do something domain transfer between two artists, they may no longer exist at the same time. So you wouldn't be able to have these examples. Again, the key contributions of this paper are that it develops an instance augmented neural architecture. And it translates an image and a corresponding set of attributes, which are these segmentation maps that we'll see examples of. It also has a context preserving loss, and the context in this case is the background. So it preserves the background while transforming the target instances. And then it also develops a sequential mini-batch inference training technique, and that's a kind of a practical technique that allows it to do training on subsets of the data rather than have to use the entire data set, which would not be practical due to GPU memory constraints. So here's some terminology that it's used a lot, and I'll just go in the paper. Also, I'll just go through the terms here. So domains, we've got two domains, and we want to learn a mapping between the two. And the mapping should preserve the target scene elements while also preserving the original context, which is the background image. So the script capital X and the script capital Y are the nomenclature used throughout the paper to delineate or to name these domains. So finding this mapping, you can formulate it as a conditional generative modeling task. So where we would try to find conditional distributions. So the probability of X given Y and the probability of Y given X. If we can find those, then we can essentially, we would have a generative model. But in the unsupervised case, we want to rely only on these marginal distributions. You know, the domain distributions, P script X and P script Y. So we don't want to have to use the joint distribution. So this above formulation, it doesn't really have sufficient information to come up with a useful mapping. So we have to provide it with more information. So what we'll do in the paper is to augment these original images with instance attributes, which are segmentation masks. And then we can improve this image-to-image translation task. And again, these additional information takes the form of segmentation masks. So here's an example with attributes, our segmentation masks. So we have on the left image pair, we have the domain of zebras. And on the output domain, we have the domain of elephants. And these image pairs, we have the original image, which, you know, color, so 3 planes. And then the mask is something the same size as the image, but binary. So more introductory material that sort of required terms in the paper is the CycleGAN. So InstaGAN uses the CycleGAN as a component of its transformation. It's a component mapping between these two domains. So the CycleGAN, it's simpler than InstaGAN. You know, it's not using augmented domains. But in the CycleGAN, there are 2 mappings, G from X to Y and G from Y to X. And we want to develop these mappings such that this cycle loss is minimized. So this picture below depicts this cycle loss and a little bit in the transformation. So on the left, we have the domain, the input domain X. On the right, the output domain Y. And G, X, Y goes from X to Y, these domains, obviously. And then GYX in the opposite direction. So in this picture, we have a blue dot X, which is transformed into the Y domain as a red dot. And then the Y hat, which is this red dot, is then transformed back into the X domain. But it's not a perfect inverse transform. There's a difference between the two. And that difference is the cycle consistency loss. So that term is used for part of our loss in training. So this picture that shows this transformation of X through two transforms back to itself. It's analogous to learning an autoencoder. But we're explicitly specifying the forms of the mappings between the domains, as well as perhaps analogously this bottleneck space. So in autoencoder, you go from a high dimensional domain, like an image domain, with lots of dimensionality based on the number of pixels. You go to the autoencoder goes to a lower dimensional vector space, and then back up again to the image space again. So this is a little bit different from that, in that this middle layer domain is the same dimensionality as the others, but there are constraints to these mappings. So that's perhaps the analogy with the bottleneck. Within the G, Y of X, there are constraints. So in the next slide, I'd like to go again, talk a little bit about these individual terms again, and some more a diagram that shows how these functions interact. So images are augmented with attributes using segmentation masks, of course. That's shown in this diagram by color images, and black and white are the segmentation masks. So the left column is the input augmented space, and the right hand column would be the output augmented space. And the transformation GXY goes from the input space to the output space, and the opposite GY X goes the other direction. In this mask is really a set of masks. So that's indicated by this bracket, sort of set brackets. And just notationally, this input is a cross product of sets. You know, you have the image sets crossed with the attribute set. So points in that set are ordered pairs. So it would be a specific image and a specific set of attributes would be the points in this space. So in addition to the generator, the two generators, GXY and GYX, we also have discriminators. And discriminators determine if the data is in the target domain. And they act like binary classifiers. The discriminators measure the output of the generator to see how close it is to the target domain's distribution. So the discriminator is an adversary of the generator. It tries to detect when an image is synthetic, while the generator tries to produce an image that will not be classified as synthetic. So there's an adversarial relationship between the generator and the discriminator. And so that's the A within GAN, you know, generator, generative, adversarial network. So More terminology that we'll need to actually build the network. So we talked about the generators, G of X, Y, G, X, Y, and G, Y, X, and their inputs and outputs. The discriminator, DX and DY. So the discriminator for the domain X has the identical input as the generator, but its output is basically the class, whether it's X or whether it's not X. The same for Y. It has this. The discriminator for Y has the same input as the generator from Y to X, but it's a binary classifier. So in order to train this system to pick the best generators and discriminators, we need to define a loss. So the loss that we're going to define is the InstaGAN loss, and it's the sum of 4 components. One of the components is the domain loss, and the next group is the content loss. So these 4 components are combined together with weights. So these are the essentially hyperparameters of the learning process. These lambdas, they allow different emphasis on the losses. So I'll go through these losses kind of quickly. I'll start with the cycle loss, which we've actually seen just a couple of depicted just 2 diagrams. This is this distance between these points after going through a cycle of transformation. And mathematically, you can see that the first term is transforming in one direction and then transforming it back, and then the difference between these 2, and then the L1 norm. So you can think of these as perhaps matrices that you're subtracting the elements element by element, and then the L1 norm of that matrix difference, basically the absolute value of those differences. And then the second term is for the opposite direction transform. Another one of these 3 terms in the content loss is the identity loss, and that's it's just a 1 rather than a cycle. It's just a 1 direction loss. So there's a term for the XY transform and the YX transform. Another of the content loss is a loss that's meant to measure the background, say, distortion. And that's done by looking at the differences in input and output, but only on only on a region which is considered background in both the input and output domains. So W is essentially a mask that defines the region of common background. So this circle means it's an element by element product of those 2 matrices. And again, we're using the L1 norm to turn that into a scalar for the loss. So finally, this first term is the GAN loss, the GAN or domain loss, and that takes into account the discriminator. It uses the discriminator as a measure of how well the transform does in synthesizing domain images. So there's 4 terms to that. The first 2 terms are for the input domain, the X domain, and the second 2 terms are for the Y domain, the output domain. And so the first term would, if dx discriminated perfectly, then it would produce a 1 for data in X. So that means if it worked perfectly, XA would be a 1. And if you subtract 1 from 1, you get a 0, and square it, you get a 0. So that term says there's no loss. If you've perfectly matched, the discriminator worked perfectly, so it doesn't contribute to the loss. So in the next term, we're taking data from Y, from the output, and then transferring it back to X and seeing how that discriminator works. And so its loss should have essentially the opposite effect. So those are the 4 components of loss. So it's quite a complex loss compared to, the types of losses that are typically used in CNNs. So the generator, we'll go through the details of the architecture of this generator, but just a high-level overview is that the generator is composed of feature extractors, or sometimes they're referred to as encoders. There's also image generators and attribute generators. So all of these functions are parametric, and they are implemented as neural networks. And then the parameters of these neural networks are learned. And parameter learning is done by finding the best set of parameters that minimize the InstaGAN loss. So that's fairly typical of machine learning. So this diagram is from the paper, of course, and I'll go through it in detail. I think gives you a pretty good idea of the computation that needs to be performed. So in the diagram, this left column represents the input domain, and the right column, the rightmost column, represents, say, the output domain. And as before, part of the domain is just images, and then we've augmented them with masks. So we have 3 targets represented by these masks. So GXY and GYX are composed of feature extractors and generators. So let's point those out. specifically. The image feature extractor is FGX. So that's a function. And it takes an image and returns a vector, and this yellow vector. So this arrow is, you can think of that as a function, and that's the name of the function in this diagram. So the attribute feature extractor is FGA. So there's 3 uses of that in this diagram, but this is all the same function. FGA is common. And when FGA is applied to this first segmentation mask, it returns this blue block. So that's a vector, you know, a point in a vector space. And so when it's applied to the second mask, it'll return another vector. They're depicted in this as blue to differentiate them from the image output. They're different from one another, of course, because these masks are different. So, and one stage that's kind of important to look at is this striped blue box. And that's simply the sum of all these 3 vectors. And this arrow here, that should be going underneath this box. It doesn't really go into the box. It's kind of confusing. It goes underneath this box. So now that we've done this feature extraction, we can then combine those vectors from the feature extraction layer by concatenating them to form image representations and attribute representation. So image representation is this HGX, and attribute representations are HGA, superscripted by I. So for the images, we basically have the yellow block concatenated with the striped blue block. So there are 2 parts to that vector. And then for the individual representations associated with masks or associated with attributes, there are 3 components. So again, we have the image yellow component vector. We have the striped component, which is this kind of a common sum component, sort of a generic component. And then we have the specific vector associated with each mask. So the third portion of the output is unique to the mask. And then finally, we have a set of transformations called generators. Even though the whole thing is a generator, this last portion is the what we would typically think as a generator, in that it's producing images of the same size as the inputs, or masks that are the same size as the inputs. It's useful to note that G, X, and Y, and YX are permutation equivariant to attribute set ordering. So if you permute the order of these masks, it shouldn't change the translated image. And that you can see how that would happen because you're summing these things all together, and that's the only input to the translated image. It does not receive the individual ones. So if you change the order, it has no effect on the translated image. But if you change the order, it will change the corresponding translated masks. They should produce correlated images. So even though you can think of these as functions, the actual implementation of them is more specific, and they're ResNet 9 models. So ResNet 9 has downsampling blocks, followed by residual blocks, followed by upsampling blocks. So you can sort of see that in this diagram, the downsampling and residuals are done on everything to the left of say here, and the upsampling is done by this last generator level. So the other component of this system is the discriminator. So that has to be implemented as well in order for this system to work and to be to be trained. So the discriminator encodes both the image and the attributes. And determines whether the pair is from the domain. So the components, we have the discriminator, the image feature extractor, FDX. Again, as before, it's this yellow block that takes the image and through this transformation FDX produces this vector. And then we have the attribute generators, which are, as before, produce vectors from masks. And as before, they're added together and concatenated with the image representation vector or feature vector. And then that concatenated vector is classified as X or not X. So this discriminator should be permutation invariant, right? So as before, that's done through this summation. So if you change the order of these images, the sum remains the same. And then again, the actual implementation of these functions is through a neural network, or specifically a convolutional neural network, and more specifically, the paper uses a PatchGAN, which is this 5-level CNN. So if you wanted to look at those 5 levels and how they are implemented in this diagram, the first 3 levels are used to form the features. And then these last 2 layers of the PatchGAN are used for the classifier. So training is done by minimizing this InstaGAN loss that we talked about earlier. So as in many ML learning methods, the parameters of the generators and discriminators change incrementally to reduce the loss. And the parameters of the generators and discriminators are weights within a set of neural networks. So the neural networks we talked about were the ResNet 9 and the PatchGAN, multiple versions of those. So another aspect of this paper that I won't go into much detail on is this sequential mini-batch translation. And basically, computational realization of this is going to run up simple computational straightforward implementation. Will run up against GPU memory constraints. So the Minibatch technique that they develop in the paper can eliminate those issues. So it's more of a practical technique. So the paper talks about much of the volume of the paper are qualitative evaluations, and which in some cases is good. I mean, you could probably not even read the paper, just look at the images and get a lot out of it. So we'll go into some details. Now we'll start looking at some of these images and seeing how it does. But part of the qualitative evaluation is to compare their technique, the InstaGAN technique, against the previous CycleGAN technique. And so the way that that's done is they sample two classes from various databases, and they develop an InstaGAN and a CycleGAN versions of those and compare the two. So the data sets that they're using, this clothing co-parsing, CCP, MultiHuman Parsing, MHP, and then MS COCO. So those are three examples data sets they're using. So CycleGAN, kind of a previous technique, it mainly fails. So it's interesting to compare the two. Whereas InstaGAN generates, for example, better sheep or giraffe, and it also preserves the layout of the original images, looking direction. So that's, I think, kind of seems difficult to do, and you'll see examples where it does that. And we'll also see that InstaGAN can control the instances to generate by conditioning the input segmentation masks. So you have the freedom to change the input segmentation mask and get results that are good. And InstaGAN will also work using predicted segmentation. So you don't just have to manually segment your masks. You can use predicted segmentation for something, some kind of semantic segmentation, or that can reduce the cost of collecting these image attribute domain data. So here's an example of it's the sheep to giraffe translation, and it's going to compare CycleGAN with InstaGAN, and the data set is MS COCO. So here's the original data on the left with sheep. Two different examples. Here are the masks associated with the sheep. And here is the CycleGAN output. And here is the InstaGAN output. And its associated generated segmentation masks. So if you compare CycleGAN with InstaGAN, it's dramatically better. And in the second example, you see there are 4 targets, and the CycleGAN, it's not even close to what you'd want. And the InstaGAN looks pretty good. It's also interesting to note to make note of what they called looking direction. So if you look at this example, we have these sheep, and if you look at their heads in relation to their body, they tend to be, from the viewer's perspective, on the left side. And on the InstaGAN, that's the case as well. The giraffes' heads are, from the viewer's perspective, on their left. And on the bottom example, with the 4 target sheep, that looking direction also seems to be preserved. So it's doing more than just you know, superposition of arbitrary giraffe. You know, it knows something about the input domain. So here's another data set, another translation result. This is called, this is the MHP MultiHuman Parsing. And this, the domain here are pants and skirts. So skirts to pants. Oh, I think I've reversed that. Skirts, pants. Okay, so again, we're going to compare CycleGAN with InstaGAN, and the data set, as mentioned before, pictures with multiple humans. So the original picture, we have 2 humans, and here this shows that the skirt mask worn by the human at the left. The human at the right does not have a skirt, but has pants. CycleGAN essentially does nothing. I can't see it doing anything at all. Whereas InstaGAN creates a set, synthesizes a pair of pants and puts them on this human on the left. So if you look at it, I mean, from far away, it seems like it does a good job. But if you really look at it, it's far from being like, you know, photorealistic. But in comparison to CycleGAN, it's, of course, which is, it's basically a complete failure, CycleGAN. So here's some experimental results where we're going to change the input mask and see how that affects the output. So we have the freedom. This algorithm allows us the freedom of supplying the image with a mask and seeing how that transforms the output. So the image is this color depiction with 2 humans, both wearing pants, and we wanted transform from the pants domain to the skirts domain. So on the top row, we've given it only a mask for the left human, and it generates an image with the left human wearing a skirt, but ignores the right human. The middle shows a mask with different humans selected. It changes it transforms that image appropriately. And then the last one is a mask set with 2 pairs of pants, and it works as well. So, InstaGAN, it's a novel method for image-to-image translation, and it was developed by incorporating sets of image attributes in the form of segmentation masks. The authors feel that it's generalizable to other cross-domain generation tasks, such as machine translation and video generation. They feel that future research directions could include investigating new domains and new augmentation information as well. And then this is my conclusion. It's that the images are not photorealistic, but they are much better than previous methods. Then the paper itself, it has many, many more examples of these translations. I can briefly maybe bring those up. Let's see. And so here's the full paper. And let's see, so the appendix has, significantly more examples of images being translated, and some of them are quite challenging, I think, and it seems to do reasonably well. I mean, for example, here we have sheep to giraffe, but there's lots and lots of sheep, and it seems to do well. Whereas, of course, this CycleGAN always does poorly. So yeah, I would recommend looking through the paper at the pictures, at least. They've gone to a lot of trouble to give a lot of examples. And then, as I mentioned before, InstaGAN uses a lot of pieces that other people have developed and kind of put them all together. But probably one of the most important is the CycleGAN. And so if there's a reference to the CycleGAN, which is done by a good paper by the University of California, Berkeley research group on CycleGAN. So if you wanted to read more as an introduction, I would recommend that paper. So I think that's it. If you have any questions or comments, have a few minutes, I guess, for that.
Hey, Frank, I have a question here. If you look at some of the coding translations, I'm trying to figure out how, choices, why some of the pants look like jeans and the pants look black. And I was just an inside assumption based of whatever makes it easiest the gender to trick discriminate. I was just wondering if some insight.
Oh, I see. So you're saying that when the training data is going to have all kinds of instances of pants. So it needs to pick out, they could be blue jeans, they could be black, whatever, jeggings or whatever. So it has to come up with something appropriate.
Yeah, So like at inference time, I feed in, I say turn it's into paint, how this may like blue, jegging over.
Yeah. So the mask that you're going to supply at inference time, I mean, it's going to be very generic, right? It's just going to be pants. If you wanted to be more specific, you'd have to, turn those domains into, like blue jean domain or jegging domain. So that's, as a practical way to enforce those constraints. It seems like you would have to do something like that. So I think that's a challenging aspect of this, in that they're pointing to the application of for fashion, where someone might potentially upload a picture of themselves and they want to see how they would look in, different types of clothing or shoes, for example. How would I look in different kinds of shoes? But that is, I think, pretty advanced compared to what they've done. But with enough data, it's possible using these techniques.
Thank you. Thanks, Frank.
Okay. Goodbye.